Good afternoon, everyone. Welcome to the distance learning program of Indian Institute of Remote Sensing. And today is the one of the last lecture on the thematic disciplines, that is overview of geospatial technology and its applications in the water resources sector. Myself, Dr. Praveen Kumar Thakur, working as scientist engineer SG and head of the department at Indian Institute of Remote Sensing, Dehradun. So in this presentation today, I will be giving you a glimpse of applications of this remote sensing GIS GPS technology, which combinedly we call the geospatial or the geoinformatics technology, and how it is used to solve and address various issues of water sources management, and how we are using the satellite data and integrating that satellite data with the GIS and hydrological models to solve the real world problems. So in the outline of this presentation, we'll discuss some basic about the hydrology and the water distribution, and what is the role and the water availability and its use scenario in Indian context, and few slides on the basic fundamentals of remote sensing, how the open water bodies or the solid form in form of snow and glacier, how it looks in a satellite image, both in the traditional optical remote sensing and also in the radar remote sensing. And then the overview of hydrological applications in the water sources, followed by how we integrate GIS, DEM, and water models, and what are the various applications, and how do we disseminate the information what we get from the satellites or the ground observation through the Indian water source information system. And then few studies which highlights the use of surface water, snow glacier mapping, and advanced EO sensors, including hyperspectral and radar data for water studies, and some field-based measurements which are complementary to the measurements and observations which we make from the space, and some unique case studies which highlights the role of these technology in water security. So if you see our planet Earth, we call it blue planet, and it is primarily due to the presence of water, which is nowhere found in the solar system in that much quantity, and also in all its three phases, that is liquid, water vapor, and in the solid form. And if you see this particular image, this is the Asia part with this and India at the center. However, if you see the Pacific part from the space, you will see only the water area. So that is because the entire 180-degree extent, it is almost entirely covered with the water, and that is why it is covering 70% of the land area. And in terms of the quantity, 97% of the water is the saline water, and fresh water which is not saline is only almost 3%. And of this 3%, almost 70% is locked in form of ice, seasonal snow, and the glaciers, mountain glaciers in the polar ice sheets, Himalayas and other mountain ranges, and rest is under the ground, that is as form of groundwater. And rest which is in form of water vapor or flowing in the river or in your pond nearby or the reservoirs, that constitute almost 1% of the fresh water. And within this 1% also, the lakes, swamps cover the majority of the distribution, the river constituting only the 2% of the surface water. And then we have this, because this is not static, it keeps on moving from one part of the earth to the other path through the global cycle, where one of the cycle is the hydrological cycle, where sun is providing the source of energy, and this water, once it evaporates from the oceans, or there is a transpiration taking place in the land area, either from the forest or from the soil or the snow, in terms of sublimation, it will combination of evaporation and transpiration, it will lead to the formation of clouds. And due to the coriolis forces and the planetary scale motion, these clouds they will move through the various weather systems, and then once the appropriate meteorological condition is achieved, they will precipitate and fall back as a liquid water or solid water, depending upon the elevation of the area or the latitude or the season of the particular location. And once it precipitates, it will fall down either as a snow or as a liquid water. And after achieving the various water saturation or the infiltration access criteria, it will either infiltrate into the subsurface, and then once it reaches the saturation level or the infiltration access level, it will flow in the overland and move through the river system and again meeting to the sea area. And this water balance is generally the ideal case. So, however, in case of the humans, we tend to store the water by making the reservoirs, because we want to protect the downstream communities from the floods, and we also want the water when there is no rain. That is, we want to irrigate our crops, we want water for our domestic use, for drinking and other industrial purposes. So we modify this natural cycle. And why it is important from the satellite data point of view? Because whether it is a virgin hydrological cycle or whether it is a human modified hydrological cycle, all these changes, either from these variables like precipitation, soil moisture, snow cover, snow melt, the surface runoff, so these can be monitored and modeled using the inputs from the satellite data. And even the man-made structures which are made, either the big reservoirs, barrages, or the water control structures, they can also be monitored using the satellite data. And their planning and management can also be done very effectively by using the GIS. So whenever we try to resolve any water issues at a individual house level or the city level or the river basin level, we always tend to calculate the water balance, as shown in this particular equation, where input is generally from the precipitation, and if you have the irrigation, then this irrigation will also come, and the losses will be the evapotranspiration, infiltration, runoff, and rest will be the change in the storage, either in the groundwater or in the surface reservoirs, or in case of the river system. So, if you come back to our Indian case, we are very large country. However, our population is much higher than the percentage of land area that we are occupying. And total amount of water as compared to the total water availability at the global scale is 4%, and our rank in the per capita water availability is 122. And our most of the rainfall will occur in the monsoon season, and there are some high rainfall areas, for example the western ghats, and you can also see the eastern areas of India and western Himalayas, where we get the high rainfall. And the western parts of the India and the some central parts are also under the arid category, arid condition, where we get the less rainfall. So if you see the present condition, we are almost in the equilibrium, that our estimated water demand is met by the current water resources, which is approximately 4,000 kilometer cube. However, as our population is increasing in the future, by 2050 there will be possible deficit of 327 kilometer cube of the water. And if we do not change our water use practices or plan for the future, there is bound to be have some level of water scarcity, in especially in those areas where we already have heavy water stress. So it is not just the surface water, but the groundwater also is under the considerable stress under the current scenarios, and coupled with the changes in the climate, which leads to the extremities of these weather events. So to plan these future scenarios and also meet the current needs, we need to have the accurate estimates of water availability and how this water is being used by various sectors. So in that case, our satellites helps a lot. And if we consider about the satellites, generally we have the two kind of satellites, generally the geostationary satellites and the sun synchronous satellites. So geostationary satellites, they have the altitude at 36,000 kilometers, and mostly they will be looking at a particular point, and they are generally the weather satellites. So if you want to see the clouds and other formation and the precipitation or the energy balance for the entire country at every few minutes, in that case we use this satellite data. And in case of the sun synchronous satellites, which maintains the similar kind of reflectance or the imaging characteristics throughout the year, they are more popular for the earth observation. For example, our resource landsat or the sentinel series of the satellites, they work in the sun synchronous orbit, and they will revisit a particular area either once every 5 days or the 20 days. And then depending upon the need of the resource survey, for example, for land and water it is the resource sat, and in the radar domain it is the resat series, which is now renamed as EOS series. EOS 4 is nothing but resat 1A satellite. So we had multiple resolution of the satellite data, starting from few meters to the kilometers, and at various spatial resolution. And for the weather and climate, we have this INSAT 3D and 3DR, which are the workhorse. And from the scientific mission, we also have the Saral Altica mission. And because it is the water sector, topography also plays a very important role. So we have this Cartosat 1 data, which provides us the stereoscopic views, having the two cameras at fore and after look direction, providing us the elevation information about a given terrain. So using these data sets, we can resolve some of the water related issues. And coming back to the spectral characteristics, the water in the liquid form, it will absorb most of the incoming electromagnetic waves, as seen in case of the Tehri Dam, what you see here. And in case of the snow, the solid form, it will be reflecting more. Here, this is a unique case where we have the solid form of the water in terms of snow and glacier. Then we have one pro-glacier lake, and then we have this Chandratal lake also. And these white patches, what you see, is the clouds. So this is the reflectance spectra for the surface water. You can see only reflectance in the visible domain. However, in case of the snow, we it is a high albedo, highly reflecting surface, especially in the visible domain, and it gets the absorption only in the this 1.5, 1.92, and 2.4, 2.5 micrometer domain of the electromagnetic waves. So these properties are made use in automating the process of surface water, and also the automating the process of the snow cover estimation using the time series or the single satellite remote sensing data sets. And remote sensing, as I told, it is used for the multiple purposes. If for example it is a geostationary satellites or the other satellites in the even in the optical domain, they provide us the precipitation, either rainfall and snowfall. And I will show some of the next slides. Satellites like the GPM, which are working in higher frequency domain of 180 gigahertz, they also provide the snowfall rates in addition to the traditional rainfall rates ranging from 10 to 25 kilometer grid size. Then we have this water bodies, where we can monitor them on daily to 5 daily basis, depending upon the type of satellite data what we are using. And it includes normal reservoir monitoring, and also the flood mapping in case of the monsoon, where predominantly the radar data will be used. Then you have in the high altitude area, Himalayan region, we have the automated the snow cover, snow parameters, and the glaciers monitoring. And in the predominantly, because India is one of the most water developed nation, where a lot of irrigation related projects are there. And for the irrigation, the estimation of the water requirement for the crops is the primary input, and for that you need to estimate the evapotranspiration. So indirectly, by measuring the land surface temperature, albedo, leaf area index, normalized difference vegetation index, by using this you can calculate the evapotranspiration, and then you can get it on daily to 10 daily basis. Then there are some non-imaging satellites like the traditional microwave altimeters and wide swath altimeters like the SWAT or the SAR system, which can also provide us the information about the water level from the satellite data. And this water level combined with the digital elevation model and rating curves can give you the estimate about the volume of the water plus the changes in the water level on the river by adding the this rating curve to get the discharge. Then this microwave, both active and passive, they are sensitive to the soil moisture. So this soil moisture is also available as a daily product. Topography plays an important role. Topography is also provided from the digital elevation model. And once you know the crop acreage area, crop water requirement, you can also estimate the irrigation water requirement. And it is also used to identify the various sources of the drinking water. So depending upon what scale you intend to work with, if you are working 1 is to 2 lakh 50,000 scale, you can go for the IRS AWIFS data sets. And in future, even the list 3 satellite data will have similar kind of wide swath and high repeativity of almost 3 days, which can be used for regular monitoring of forest, agriculture and the wetlands. Then we have the list 3 if you are going for the mapping scale of 50,000, where it is very good for the reservoir monitoring, command area mapping, flood mapping and the monitoring. And this is the repeativity and the swath of these satellites. In future, this swath is also going to increase. Then we have this list 4, as per the new geospatial data policy, data up to list 4 sensor, where you can go up to mapping scale of 1 is to 10,000 scale, can be can be made available freely to all the academic and other government users. And if you go for the 10,000 scale, you will be able to see various ponds, check dams and field level crops. And still, if you want to go for the higher resolution, you can go for the cartosat series, where you can go for 1 is to 5,000 scale, or the cartosat 2 3 series, where you can go up to 3,000 scale. If you want to go below this, then we generally prefer the use of unmanned aerial vehicles or the drones, but they will have the small area coverage. And once you have all kind of satellite data, and then how do we derive the information or develop a knowledge base out of this huge amount of data sets and the information? So the answer, for the most of the water studies, we have to define a geographical unit, and most of the time that geographical unit is a watershed, which is a common geographical area draining to a common outlet. And this watershed will have various characteristics, both physical and climatic characteristics. These physical characteristics like the elevation, land use, land cover, the soil, generally they have the changes in the xy direction, or the z direction. That means they are changing more in the spatial pattern rather than changing with the time, for a small monsoon or the annual or the seasonal scale. However, this climate will vary both seasonally, temporally, and spatially, and it can vary within few hours to within few minutes. So these both data sets, climatic and this physical characteristics, can be represented by combination of raster data sets, for example land use, elevation, and some of the vector data sets like representing points, lines and polygon of hydro points, drainage network or the catchments. And they all have the common information of latitude and longitude. And once we add all these data layers at a common projection system, then we make a virtual reality. These days we call them the digital twins, for a given watershed, city or a basin. And then once it is, data set is ready, then we add some mathematical equations to simulate the hydrological cycle components, which is popularly known as the hydrological modeling, or the various scenarios that if you have X amount of rainfall, what will be the amount of runoff that is expected to come in a given point, or what is the if there is a dam breach, for example, in the Lonak, or the other cases of the reservoir breaching. So, how much water is going to come in the downstream area, and what are the areas going to be inundated? So, that is the role of these process based models by integrating various geospatial data with some mathematical equations for the water flow. So, this is the summary of what we do in the water sector, and this is a representative image where I am showing you the catchment area of Asan watershed with the black line. And this typical watershed, because our city Dehradun is part of Ganga basin, and this city is acting as a ridge line. The water to the west of this city is going to the Yamuna river through the Asan river watershed, and the water from this river to the east of it, it goes to the Song river catchment, which meets at Rishikesh. So we have two river sub basin, Upper Ganga basin and the Yamuna river basin, which is drained by this city. And this various hydrological problems which are multi-scale, either at a city scale or small sub-watershed scale or at the basin scale, we can address these problems. And then there are some hydraulics problem which try to address the flow of water either in a small river or in a small stream, or in the urban drainage system, or in case of urban water distribution system. So all those problems can also be addressed. Then you can also see the man-made structures, like two barrages are there, this Dak Pathar and the Asan barrage, connected by a power canal, which is diverting the water of main Yamuna river at Dak Pathar, and then this water gets transported through this power canal, and in between also we have one small hydropower station which is maintained by and operated by Uttarakhand Jal Vidyut Nigam. So this whenever we make any hydraulic structure, the first criteria is what should be the design flow. For example, for the safe discarding of excess flood water, and also to maintain the minimum level of water for power generation or meeting the other objectives of a project, whether it is irrigation, flood control, or the power generation. So those information can be derived by making the GIS models into the these projects sites. Then the traditional method of calculating the length of the canal, the area of the water spread, and how much volume is there within a given water body, those calculations can also be done. Then if you see this image closely, this particular line is the Asan river, and the light green color what you see is the agricultural crops, and this green color is the sal forest. And these two tones are one is on the north of ridgeline, one is on the south of ridgeline. They represent the Shivalik mountain range. The northern side have more moisture, so it is a moist deciduous forest, and the southern aspect of this Shivalik range, it drains to the Solani watershed of the Ganga river. It is having the dry deciduous forest, because in the winter it will have the leaf shedding. And this water what you see here, these lines are the ephemeral rivers. So what you see, this blue line here is the groundwater, so it is a February image. So in this case the groundwater is coming out here, and it is representing one of the groundwater heads when we do the groundwater modeling. So how we can integrate the surface water and groundwater resources, that can also be done. And finally the irrigation water management, because we know the how much area of the crop is grown, what kind of crop is grown, and we know what will be the crop coefficient or the evapotranspiration for a particular day, if I can get the thermal data from the satellite images or albedo or NDVI. So all the water needs and uses and the spatial variability of these features can be integrated. So this whether it is hydraulics, hydrology, environment or groundwater, we try to integrate them in GIS and to give scenarios and set of solutions and option to the decision makers. And coming to the satellite data, how it looks in the headwater basin. This is single pan images where each individual band is shown in a grayscale. Whenever you download the satellite data, these days many people directly start using the Google Earth engine to see the satellite images, or those who are starting the remote sensing, they simply start with the Google Earth. So what you see in the Google Earth engine or Google Earth is the final processed product. So when you do the imaging, there are set of cameras, various filters, so which are viewing the reflected energy from the sun in various multispectral bands. So for example, this is example of Sentinel 2 images, where this is a 490 meter, 560, 665, 705, that is the visible domain, and then you have this NIR domain here, and then this is the SWIR domain. So for the upper reaches of the Ganga basin, so if I combine various SWIR band, NIR and the red band, we get the color composite something like this. So this is the starting point of the Ganga river. This is the Gangotri glacier, and this is the Bhagirathi and Alaknanda glacier. This side it known as the Alaknanda river, where my mouse cursor is there. And let me add the pointer. Yes. So this is the pointer here, and this is the Alaknanda. Here we have Badrinath somewhere here, and on the southern aspect of the ridgeline of the Gangotri glacier, we have this Kedarnath Valley, and these are the elongated watersheds. So you can see the glaciated areas here. Now some of these glaciers have already receded. Instead of having the single glacier, this is the point where we have this Kedarnath temple here. And if you go further downstream of this Gangotri glacier, this particular point is Gomukh here, and this particular point, if you go this here, this is the Bhojbasa, and 14 kilometers from the Bhojbasa we have the Gangotri temple. So the water in the Himalayan river system, they originate from these kind of glaciers, and the ridgeline between this Gangotri and this Alaknanda Bhagirathi glacier is known as the Chokhamba. So this is somewhere we have this Chokhamba ridgeline, and because they are at very high altitude of 7,000 meter to 4,000 meters, the water generally will precipitate as a snowfall for most of the cases, whether it is summer or in the winter. And due to the valley shape of this one, it keeps on accumulating the ice for thousands of years, and this ice, by the way of gravity, it flows as a river system in the downstream, and the point where it starts flowing as a liquid water is known as the snout, because that position we have that triple point condition of the water getting satisfied. And these glaciers in the mountain valleys, they are generally the debris covered glacier, that is why this kind of reflectance. And in the up area of these glaciers, this Gangotri is the second largest glacier, having almost 36 kilometer of the length. In the upper reaches, the ice is overlain by the fern or the seasonal snow. In the downstream area, that seasonal snow will melt away, and the debris covered ice will be seen. And then if you see the animation of these glaciers, by combining georeferenced images of this glacier for last 20 to 30 years, we can visualize why we call them the moving river of ice. So they are always moving in the downstream direction, and sometimes if you focus your location here, many a time in the literature we say they are retreating. So they are retreating because the net melting of the glaciers is much higher than the net forward movement of the glacier system. And except for the Karakoram, where we do have some surging, most of these glaciers they recede at the rate of 15 to 20 meters per year. But in the upstream areas, this velocity of the glaciers can be as high as 70 to 100 meters per year. And this kind of time series, this is in the animation, but quantitatively also, by using the feature tracking or using the radar interferometry methods, we can estimate the velocity of these glaciers. And then using this velocity, there are some inversion models which give us information about the depth of ice which is present in these glacier systems. And then the water which is coming to the Bhagirathi river at the Gomukh, it is predominantly the melt from the glacier. However, this percentage of the glacier melt, it can be 5 to 30% depending upon at what location you are in a catchment. But overall contribution to the water of these Himalayan rivers comes from the seasonal snowfall and the subsequent melting in the spring season. So you can see here, this is for the Himachal area, and this is the animation which has been generated using the satellite derived snow cover on weekly basis for the entire northwest Himalaya. So depending upon the relative height and the permanent glaciers, the minimum and the maximum snow cover in a given basin will vary. For example, here what you see, Chenab basin having the very high percentage of minimum snow cover area and also high percentage of the maximum snow cover area. That means it has a much higher contribution of snow melt and glacier melt as compared to the Beas basin or the Ganga basin. Then because we want all weather capability, it is not just the monitoring, because from the disaster point of view, from the defense point of view, we need to see these glaciers, whether it is cloudy condition or whether it is snow condition. The same Gangotri glacier in the monsoon or in the winter, it is very difficult to recognize, but in the radar images, because they are not dependent upon the reflective energy from the sun, which is detected by the remote sensing sensors. They generate their own electromagnetic energy in terms of the electromagnetic wave, most popular being the C band, that is 5.4 gigahertz, and they send this electromagnetic wave in a inclined angle. They interact with the ground surface and then come back towards the radar, and by using various Doppler processing and various Fourier transforms, so we convert this signal into the image by converting this signals by inverse FFT transforms and this single loop complex into the amplitude images, or using various image radar decomposition techniques. For example, here we have used the MKE decomposition techniques to see the underlying terrain. So in the peak of the winter also, I can see the clean ice glaciers. The debris will have the higher scattering as compared to the clean ice, so it is distinctly visible. Any other glaciers on the other side also in the Kedarnath valley are also visible. Supra glacier water also lakes, they will also be visible very clearly. And recently we had this disasters of Lonak Lake, and fortunately the day it got breached, at that time our EOS 4 had a satellite pass. So this is used to monitor the subsequent change in the volume of the glacial lake, and this is the debris covered glacier, debris from the ice debris which is floating on the ice. And it happened in the middle of the night, and the image was taken at 6:30 in the morning. So you can also see the flood marks which is much higher as the photograph is taken in the morning. So these kind of disaster monitoring from the space also, it is very much part of all our standard operating procedures. And on that day, 4th 5th of October, we got lucky that our satellite pass was there. However, there are some constellation planned from the new space companies or the private companies which can monitor any part of the globe on almost daily basis, and sometimes on hourly basis also, depending upon the request from the users. And you can see, because this last 30 years data is publicly available either through the Google Earth Engine or from the original data providers. So you can see during the construction of the Tihri how it was the terrain in 2000, and after the filling of the dam how much water has been stored here, and this total area of the watershed by using the popular indices known as the normalized difference water index. Then, as I told, in the floods also we need to monitor how much area gets flooded for conducting various relief operations, and also providing the flood damage assessment to the relief commissioners of the state. So our center at National Remote Sensing Center Hyderabad, they do this work operationally for all parts of the India, and they have been doing this for last 30 years, and many states this flood hazard atlas has been released. This is one more example for the 2008 Bihar floods, where there was a breach of the barrage at the Indo-Nepal border, and the Kosi River followed its historical flow path from directly coming from the north to the south direction instead of moving the westward direction. And as I told, these days from the Sentinel-1, which is a publicly funded satellite program under the Copernicus program of ESA and the European Union. So this data has been kept as a open source data in the Google Earth engine. So if you want to do the flood mapping using this data, you can do it very fast, and you can get the first hand information about the inundation area. Then there are some advanced sensors like the hyperspectral sensors, and most popular of that being the IIRS NG, which is a joint collaborative project between NASA and ISRO. So this hyperspectral data will collect the same information, but at much higher number of wave lengths and number of channels, more than 200 wavelengths, and you can see the very sensitive part of the whether water, mineral, or the ice. So for example, in this case, all this effects of the turbidity which is coming from the sediment laden water in Chelka lake, it is getting very much reflected, and this relationship is developed between the turbidity and the reflectance, and it can be automated by using such kind of data sets. So all this information is kept at the central site, and it is one of the success stories of two government departments, for example, Central Water Commission and Indian Space Research Organization joining hands to make the one of the most popular and successful web GIS portal known as the Water Resource Information System. So it was created with a joint collaboration, and now it has been fully transferred to CWC, working under the National Informatics Water Informatics Center, and new website has also been launched. And all the river basin atlas, watershed atlas has been prepared, and they are available for all the users to access with some area limitation. Many times researchers or planners, they do not have the clear idea about the where we are measuring the water, how much water we are measuring, what are the locations where these structures are located. So this portal has eased that way by providing all the geotagged information about the location, and there are some classified basins, there are some non-classified basins, but the location of all the gauging sites and the structures is easily available. And if you want to order the data from any of these basins, whether classified or non-classified, you can make use of this portal. And then we have this irrigation, one of the largest user of the water, whether India or in any other part of the world. So this is one example where the reservoir is there. In the downstream you can beautifully see the canal network, which is part of a particular irrigation command area. And then once the crops are grown in the traditional FCC, they will be having more reddish kind of tone. So that can be mapped every 5 to 23 days. And on the right hand side, what you see is the Burla irrigation command area just downstream of the Hirakund dam, and there it is the three times the rice crop is grown. So you can see, because for the rice crop you have to do the surface flooding. So few initial months it is almost the cyan color, and then later on, depending upon at what stage the crop was grown, some area it is showing this reddish tinge. Then this upper area, it is shown early as compared to the downstream area of this Burla irrigation command area. And then the growth or cycle of a particular crop is also very clearly seen here, and by the end this entire area, upper area, is more grown as compared to the downstream area. That is true for all the command areas. The headwater command area receive more water earlier as compared to the downstream areas. But this full monitoring is very effective, and then you can quantify how much water is being used by capturing these images in various times and inferring the land surface temperature, the albedo and EVI, to calculate either crop coefficient or calculate the evapotranspiration. Then using the high resolution satellite data of Cartosat series, CWC and World Bank has given the project under the EIBP project of World Bank, and they give the funding, provided that you provide the proof that you have constructed the canal, you have repaired the canal, whether it is a major, minor, or the field level tributary. And these data sets and this project EIBP phase 1, phase 2 has been monitored by using the high resolution satellite data. And this is just example of two irrigation command areas in Upper Ganga basin, which was monitored using the Cartosat series. And then once this data set is there, this is hosted in the Bhuvan website also, and all kind of network analysis can also be done here. Various analytic skills, for example, you want to know what are the areas in your network where you have the crossing of the road, or what are the number of branches where you have. So all these analytics can be done very easily once you have this GIS database. So this entire, because we have a large number of irrigation projects in our country, so the digital version of this, it is being actively done by CWC with the help of ISRO or other geospatial agencies. And then this data is the backbone of all our irrigation scheme, for example under Pradhan Mantri Sinchai Yojana or any other federally funded irrigation projects. So in form of research in the hydrological cycle, so in the second slide, in introductory slide, I have shown you that we try to understand and monitor the various components of the hydrological cycle. So it is the representation of the same, where the various variables and the factors of hydrological or the water balance, they are represented by satellite. For example, precipitation, we do some TRMM and GPM or megatrophics or INSAT series. Evaporation, we use the energy balance satellites. For the discharge, we use the altimeters, and for the snow, we use the Saral Altica, or the Modis. For moisture, we use the other set of satellites, because these days the satellites, they are not just used to see what is there on the land, but also do some geophysical measurements. So these satellites are dedicated to a particular geophysical parameters. In this case, it is related to hydrological parameters. For example, ASMOS, it is focused on soil moisture. Altimeters, they are focused on surface water. The GRACE, it is focused on the groundwater. So this is the trend, and in the future also we will have more number of, because our these variables, they are not static. They can vary on hourly basis, they can vary on daily basis. So in future, techniques are already developed, very mature. So what you see, the constellation of these kind of satellites, so that your temporal resolution can be taken care in case of the hydrological cycle elements. So this is just glimpse of the precipitation which is given by INSAT series of the satellites, and these algorithms are developed at our Space Application Center, Ahmedabad. The three algorithms: quantitative precipitation estimate, hydro estimator, and this IMERG program, which is transferred to IMD for the operational estimate of the precipitation for the entire India from the INSAT Kalpana series of the satellites. Then you have this constellation of the satellites, where not just the optical data or thermal data is used, but the active and passive microwave, plus the radar data from the GPM is also used. So because it is one satellite can view in this particular orbit maybe 4 times a day or 5 times a day. But if you want to get the daily rainfall, you need to integrate and assimilate the information from all these satellites. And this is just a tabular form where number of satellites are given, which are used to generate the global product. And this global product is available at 10 kilometer scale, and it is available from 2015. And the latest version of IMERG, it is they are doing the reprocessing of the precursor of GPM, that is the tropical rainfall measuring mission, which was the first satellite which was used for measuring the precipitation. So they are processing that data in that version 7. I think by this month it is going to be released. So you will get this zero point 0.1 degree at every half an hour from 99 to till now. So almost 25 years of the satellite derived rainfall you can get at very high spatial and temporal resolution. And there are some other sources also. For example, the same GPM satellite from the Japanese GS map series, and for India also this JAXA and ISRO, they have joined hand and they are making a new improved satellite rainfall product by combining the IMD data. And there are some Aphrodite, Persian, and CHIPS data sets which are very popular among the academic community. Then from the river water level or the water level in the reservoirs, so we do different kind of remote sensing. Instead of getting the sun illuminated reflected energy, or seeing the synthetic aperture side looking radars. So if you have a radar or if you have the laser in space and it is nadir looking, so in that case it will emit the electromagnetic waves either in microwave frequency or in the green or IR frequencies, and then it will interact with the surface. And if it is water case, and we will measure the two-way time travel, and then we know the height of the satellite, and in between we have the atmosphere, so we make correction for the atmosphere, troposphere, and then we can estimate the height of a particular terrain. And if I make this time series, and if there is a change in the water level in the river or in the reservoir in the pre-monsoon and post-monsoon, so I can make the time series of the water level with respect to some datum. So this time series of the water level will give us by combination of rating curve the volume, that is the discharge coming through a cross section, or if it is a reservoir, by using the trapezoidal formula, the volume in the reservoir. So this is a very effective and very important technique which has matured in last 20 years. And the future of that is, currently we have a one dedicated satellite which is known as the surface water and ocean topography mission. And this mission is a significant improvement over the traditional altimeters. It does have a traditional nadir looking altimeter working in KU band. However, it has a KA band interferometric radar also. So in the interferometric radar is like in the optical parlance, for example, cartosat having the two tilt angles, and from the single satellite I am able to generate the stereoscopic view. So before that we had such kind of mission in space shuttle radar topography mission, popularly known as the SRTM. So in that data also it was very difficult to generate the water bodies elevation. So there was some error, but because their baseline was almost 60 meter, but in this case it is a 10 meter baseline and it is working in KA band. And KA band is sensitive to the surface water, and you have this near swath 10 to 60 kilometer, and it is transmitting, and the other this one is also receiving the signal. And left rooking and right rooking, we have the 2 meter to 70 meter near range and far range resolution. So using this synthetic aperture radar setting, you can get the elevation of the water bodies, elevation over the water bodies. So this is basic principle of wide swath altimetry. And once the calibration process is complete, so all the rivers having width of 100 meters or higher, you will get the water height, width, slope, and discharge. The water discharge as a product from this satellite, and then there are the other products of the 200 meter at giving the river height and the width, and the changes in the lake storage and area for all the water bodies which are above 6 hectares. So this is a one significant improvement on the monitoring of the surface water resources, which this satellite has promised to deliver. And then the other part, which is part of our storage capability, known as the soil moisture, which is also very important from the agricultural water management point of view, and also the flood control. So the satellites, mostly the micro satellites, were sensitive to the dielectric constant and the roughness properties. So this is the example from passive microwave satellite, where almost a daily basis we get at 25 kilometer the changes in the moisture. And active microwave is also equally sensitive, giving at high resolution. So this was the ideal mission known as the soil moisture active and passive. So we have this L band, which is a high frequency, this is a low frequency high wavelength sensor which can penetrate much more in the soil. And for the water we were using Ku band, where it was high frequency low wavelength, and in case of the surface penetration we use the soil moisture, for use the L band. So it gives the both radiometer and the radar in the single satellite. And now, due to some malfunction in the radar point, they are filling the gap with the Sentinel 1 C-band data to give you the users the continuous time series of the soil moisture. And by using some land surface models, this soil moisture data can also be converted into the root zone soil moisture, which is given as a level 3 and level 4 product from the this space agencies. Then the other part which is important from the water management point of view is the evapotranspiration. So there has been significant progress on this domain also. The primary driver for the evapotranspiration estimation is the thermal data sets, which is publicly available through the Landsat series of the satellites. For example, the Landsat 8 and 9 series, and now we do have this our OceanSat series also, which is giving us the thermal data sets, that is EOS 6, and the Sentinel 3 also is having the thermal. Modi's satellite data, it is also having the thermal band. So this thermal data along with the other energy balance models like the Siebel or the metric models, they are available in the Google Earth engine. So you can run them directly and compare it with the ground observations. Then for the surface runoff, it is one of the oldest method, known as the curve number method, or the SCS curve number, now known as the NRCS curve number method, where we combine the land use and soil to give you the hydrological soil group. And this hydrological soil group is again function of the this curve number. And higher the curve number, more will be the runoff, and runoff is calculated using this empirical equation. And because from the satellite data we do get the land use land cover at every 5 year, and sometimes on annual basis also, and soil usually they will not change. So these days, from the global soil resources grids, this is available at 250-meter resolution also. But from Indian land use and soil surveys, it is mostly available at 1 is to 5 million or 2 lakh 50,000 scale. And the groundwater is equally important, because not all the rivers in the India are rain fed. So there is a heavy dependence on the groundwater also. So in 19 early and this 1983-84 there was a big drought, and then 86-87 there was a floods. So government of India at that time they asked about the whether satellite data can be used to identify the locations where there is a high possibility of getting the groundwater. So this is the project known as the National Groundwater Mission. So under this, various geological features, for example lineaments, valley fills, abundant floodplains, paleo channels, dikes and folds, they can be interpreted. And then combining these hydrology maps, lithology maps, structural geomorphology, depth to the groundwater table, you integrate these GIS layers, and then run some multi-criteria process. And this atlas is available at 50,000 scale, and this has been used by many state agencies to dug the bore wells and identify the possible locations so where there is a high probability of getting the groundwater as compared to going in the field without any knowledge. And then there is a one unique satellite which does different kind of remote sensing. It is not the optical, thermal or microwave or the altimeter. It does a measurement of the gravity by accurately measuring the location of the two set of satellites. In this case they are known as Tom and Jerry, and the location is very accurately mapped by using some laser sensors which are locating these two satellites in between them, and also they are having the GPS sensors. So any change in the gravity or the mass, it gets reflected by change in relative position, and this changes in the mass, the water cycle or the groundwater represents the most cyclic of these changes. So depending upon how you solve this water problem, it is the terrestrial water storage, which is a combination of groundwater, snowpack, surface water, and the soil moisture. And if you want to infer the groundwater, if you know about the other components, you can measure the groundwater. And this is because it requires a significant mass, and generally before this GRACE satellite, it is used by the mineral and oil exploration companies, those who or the geodetic organization of the country, where they used to do the aerial surveys for the gravity anomalies. So now when we do at global scale, so the resolution will be 100 kilometers or higher. So once I know this total terrestrial water storage, I can infer the soil moisture, soil water equivalent, evapotranspiration runoff, depending upon what parameter I'm interested in. And this is some of the results from the terrestrial water changes on the global scale. At monthly scale it is available, so you can see the northern part in month of May, it is highly water stressed, as well as the Greenland ice sheet, which is having the lot of melting taking place, because this is also giving the changes in the gravity due to changes in the surface ice. And this is a small movie where it has been made to see the changes in the elevation at various continents by making this time series. Now it was a GRACE during the initial years. Now it is the GRACE follow-on mission from I think 2010-11 onwards. So you have almost 20 years of continuous coverage of this terrestrial water storage from space at continental or the regional level on monthly scale at 100 kilometer or higher. Then you do make some ground measurements. For example, the water sector volume is the unknown parameter, so we do have to conduct the bathymetry survey, or the water carrying capacity in the river system. You have to conduct the cross section survey, so you make these measurements. And then once you have this, so this is the schematic how we do the hydrological modeling or the flood modeling by integrating all these data sets. And then because the high mountainous regions like Gangotri, they do have this geomorphological hazards or the glacial hazards. This is one hazard happened in 2017, where a lot of debris flow has taken place in monsoon of 2017, and this entire section was breached, and this water which used to flow in the center line, it moved towards the right hand side of the river. By using the drone survey and by using the process based models like the RUMS model, we also simulated how much debris were deposited and how much it was eroded. Then this is for the Lohanak Lake. Lohanak Lake, unfortunately, it was well known, well published, well documented that this lake, if may breach how much area. This is that same dam Tista 3 project, where it got simply removed by heavy flood flow from the Lohanak breach site, and there was an attempt to lower the water level by using the siphon, but it didn't work fully. And unfortunately that heavy monsoon rainfall came this season itself, and that lake got breached. So to solve this, generally we go for the early warning. So in the early warning, it is the meteorological forecast which is that first, and then that meteorological forecast gets translated into hydrological forecast, and the hydrological forecast gets translated into the inundation forecast. So this is the complete cycle. If we do properly with the fair degree of accuracy, we can forewarn the people who are living in the low-lying areas that flood is going to come at their home or at their properties. And this is one example of last year floods of Uttarakhand, where um, this area is known for this Song watershed of the Dehradun, which is draining to the Rishikesh. It is well known for such kind of heavy events. So you can see here before and after flood in 21st of August 2022. So although damage is reported in this Mal Devta area only, because there were some human settlements, especially the commercial ones, which were created very near to the this natural floodplain of the river. Then many cities in India, they see the urban flooding. So urban flooding is basically increase in the impervious area, as we can see from the satellite data. And this impervious area reduces the infiltration and increases the surface runoff, and that peak discharge is very high. For a small city like Dehradun, the peak discharge of these small rivers is as high as 400 meter cube per second, and that will be there within few hours. So, and then there is a problem of drainage congestion due to the unauthorized occupation of these floodplains and dumping of the debris and the solid waste in these natural drains. And then apart from these models, you can also go for the integrated fully storm water management models, which is again example of the Dehradun city. And we can identify these red areas which are showing the areas or the wards which gets frequently flooded in the monsoon season. And then apart from the flooding, as I told, the water distribution network modeling is also feasible by using high resolution satellite data and combining ground observation data sets in a GIS format in the models for water distribution like EPANet, which are freely available, and to see which areas require augmentation of the water or the replacement of the pipes, or reduction in the water losses, so that they get 24-hour assured water supply. So with this, I thank you. The next mission, which is very big from the Earth observation, including water sector, is the NISAR mission, which is the NASA ISRO combined SAR mission, and the SWOT mission is already there. And once its calibration phase is over, you will be able to see river discharge and the changes in the water volume of all the water bodies at a global scale. And in the NISAR, this changes in the groundwater due to the subsidence or the groundwater withdrawal, the cryosphere, the ecosystem, soil moisture, wetlands, all these will be given as a level 3 or level 4 products. So with this, I complete my